Hello everyone. In this lecture, I will be discussing about very advanced technological advancement in radiation therapy, radiation oncology, called the high dose rate brachytherapy. This is a little something different than the external radiation therapy, which I discussed in my previous lectures. Now let's talk about the HDR brachytherapy. Okay. So before I formally begin, let me ask you a question. Okay, suppose if you want to heat only the center of the pizza without heating the entire kitchen, what you do? Would you place the heater far away in the room, or would you place the heat source directly near the pizza? Of course, you would place the heat source close to the pizza, right? The target. That is exactly the brachytherapy used. So instead of sending radiation from far away, just like in external radiation therapy, we bring the radioactive source directly near or directly into the tumor. Okay, so here the term brachy, if you see the term brachy is the Greek word. So brachy means too short. Okay, too short. That means short distance. The short distance is behind the power of brachytherapy. Okay, so radiation intensity falls off very rapidly with distance. We know that. So if we can place the source very close to the tumor, we can give extremely high dose to the tumor, but at the same time we spare the normal tissue surrounding it. Okay, so let me ask you another questions. Suppose you are standing just before the campfire. Okay, you are standing just near the campfire. If you move just a few feet away, what happens? The heat drops dramatically, right? Inverse square law, the intensity drops inverse square law. So the same thing happens in brachytherapy. The steep dose fall off. Okay, this is one of the greatest advantages of brachytherapy technique. Okay, so according to the International Commission of Radiation Unit and Measurement, that is called the ICRU. Okay, what do you mean by high dose rate brachytherapy, HDR brachytherapy? So ICRU define HDR brachytherapy as this. It is defined as the brachytherapy technique deliver at dose rates greater than the 12 gray per hour. Okay, that means 20 centigrade per minute. If you convert that into centigrade in minute, 20 centigrade per minute or greater than that value. Okay, that kind of rate, if you deliver that, then this brachytherapy technique is called the high dose rate brachytherapy. Okay, in contrast, low dose rate brachytherapy, low dose rate brachytherapy, that we call the LDR brachytherapy, delivers the radiation at dose rates between 0.5 to 2 centigrade per minute. I think if you convert into the gray, it may around 0.4 to 2 gray per hour. You can change that one. Okay, so depending on the rate, you can define the technique in brachytherapy is the low dose rate LDR or the high dose rate SDR brachytherapy. Okay, so let me go a little bit about what do you mean by LDR and SDR brachytherapy. I will connect with some analogy here. Okay, so let me discuss about that. So now think about these names for a moment. Okay, low dose rate and high dose rate. So what do they actually mean clinically? Okay, it is a simple analogy. Suppose you need to fill a bucket with water. So LDR is like slowly dripping water into the bucket over many hours. But the SDR is like opening the faucet strongly and filling the bucket very quickly. So both are eventually fill the bucket, but the delivery style is completely different. Okay, so historically, LDR brachytherapy requires the patient to remain hospitalized for 1 or even several days with radioactive sources inside the bodies. Patient had limited mobility, nurses minimized room entry, family visitation was restricted, radiation exposure to staff was always a concern. So we want to remove that limitation. That's why SDR is in the place here. So this lead us naturally to concept of after loading. Okay, I will use the term after loading many times. Okay, so let me ask you this: if you were handling a highly radioactive source, would you first position the patient carefully and then bring the source later, or would you carry the radioactive source around while positioning everything? Obviously. So the safer method is to position everything first and then load the source afterward. Okay, this is exactly what after loading means. Okay, so in after loading, what we do is the applicators are inserted into the patient first, right, without radioactive material. Then only after proper placement verification do you need to introduce the radioactive source. Okay, early system basically use the manual after loading, which is dangerous actually and not good. But modern high dose rate brachytherapy uses the remote after loading technology. Okay, it's like a robotic arm, to place the radioactive source into the tumor. So the source in this situation stays safely in the shielded inside the machine until the treatment begins. Okay, that's the very important thing. So here is the important clinical questions. So why did SDR become more popular while traditional LDRs become less attractive here? Okay, that's important thing to discuss. Let me think about that. Okay, suppose somebody has a patient, which would that patient prefer? Staying immobilized in hospital bed for 2 days with radioactive material inside you, inside him, inside her, whatever, or coming for a short outpatient procedure lasting a few minutes, right? Definitely, most patient prefer SDR for convenience alone. Okay, so the SDR also improve the radiation safety dramatically. How it is possible? Okay, we'll discuss about that. So the staff no longer need prolonged exposure near radioactive patients. Optimization become much better too. Okay, so the in SDR we can adjust dual position. We'll discuss about that. Okay, dual position and the dual times a very precise way. Okay, this is a technical term: dual position, dual time. Okay, think about the dual position. Okay, think of dual position like stops made by a train. Okay, imagine the radioactive source is a train traveling through the applicator. Okay, at some station the train stops longer, at other it stops briefly. Longer stop means high radiation dose in that region. This is how SDR saves dose distribution so elegantly. Okay, the common sense, we develop this technique with the common sense. Very important thing to realize here. But now let me challenge you with another question here. If SDR is so good, why do you still need LDR, low dose red brachytherapy, in some situation? Why not completely replace it? Okay, is there any chance replacing the SDR? Is there any chance to replacing the LDR by SDR? Let's discuss about that. Okay, so this is where the radiobiology becomes very important. That's why in radiation oncology you discuss much about the radiobiology. So the LDR delivers the radiation slowly over time. Slowly means it allows the normal tissue to repair, that is soft lethal damage during the treatment, right? So in some clinical situation this can be advantages. Okay, but LDR also decades. Also, if you look at the clinical outcomes, clinical experience, we have a lot of clinical data supporting the LDR, its effectiveness. Okay, especially for permanent prostate seed implant cases. For example, the iodine 125 is another radioactive sources. Okay, that is, we use the prostate seed implant that is still widely used in this clinical arena successfully. Okay, so even through even though the HDR dominates many gynecological application today, LDR remains valuable in selected disease sites. That's why it is not still replacing. But in near future, yeah, I don't think in near future, LDR will survive. Still, we'll use the SDR. SDR will replace all the LDR technique. That's what my assumption. Okay, so let me move little bit of the SDR delivery system themselves. So how it can be delivered. So the modern HDR brachytherapy treatments are delivered using a remote afterloader. Okay, a remote afterloader. Think of the remote afterloader as a highly intelligent robotic delivery system. Okay, inside the machine sits a very tiny but extremely radioactive source. Okay, during the treatment, the machine pushes the radioactive material through the transfer tube into the applicator placed inside the patient. So the historically several isotopes were used, okay, including the cobalt 60, cesium 137, but today the most common radioactive nuclei for the high dose rate brachytherapy is iridium 192. Okay, let's talk a little bit about the iridium 192. Okay, so why do you think the iridium 192 becomes favorite source than the cobalt 16 and cesium 137? Let's break it down. First, it produces the gamma rays with suitable energies for therapy. First of all, second, the source can be manufactured extremely small. Okay, that's what we need. Third, it is flexible enough to travel through the curved catheter and applicator. Okay, think about the threading a needle with a flexible wire versus a rigid metal rod. Okay, flexibility matters erroneously here. Okay, flexibility matters a lot here. Okay, so the typical SDR source, if you talk about the activity of the SDR source, is around 10 curies. Okay, that is the curies, the activity, how many decay per second. Okay, if radioactive nuclei is decaying, that the one of the unit is very high. 10 curie is very high, right? That is approximately 370 gigabecquerel. Becquerel is the unit for the radioactive activity. So this is an incredibly intense source. Okay, in fact, if improperly handled, it could deliver dangerous dose very quickly. That is why safety systems are absolutely essential in HDR brachytherapy. So let me ask you something important. If the source is so strong, what would happen if the source becomes stuck inside the patient? This is exactly why HDR unit have multiple redundant safety systems. Safety system is very important thing here. So the modern HDR system continuously monitors the source motion. Okay, if excessive friction or blockage is detected, if electrical outages happen, the machine must still safely retract the source. Okay, it must have a ability to retract the source. The backup battery acts like the emergency generator, okay, in a hospital ICU, like a hospital ICU. So the safety can never depend on a single power source like that kind of treatment. So we must have a backup. So another critical component is the dummy wire. Okay, dummy wire. What to do before the active radioactive source enters the applicator? A non-radioactive dummy wire first travels through the exact path. Okay, why do you do this? Why do you do this? Think of it like sending a scout ahead into the tunnel before sending a valuable train. Okay, the dummy wire verifies the pathway is clear without any restriction, any kinks, no excessive bending. Modern SDR units such as those from Elekta use the multiple channel. Okay, they have the multiple channel. They are connected in index system. Transfer guide are inserted into the channel. located on a rotating turret. So the machine actually rotates and aligns its channel precisely for treatment delivery here. So the position accuracy is another fascinating aspect in HDR brachytherapy. So the modern HDR system achieve source positioning accuracy within approximately, you can say, the plus or minus 1 millimeter. Very extremely precise here. Okay, so let me ask you, does 1 millimeter really matter here? So we talk about in external beam radiation therapy, maybe small error, plus minus 1 is very small error. Sometimes plus minus 1 is modest, right? But in brachytherapy, because of the very steep dose gradient, even a millimeter shift can dramatically alter the delivery dose. So imagine placing a flashlight extremely close to a wall. What happens? Even move in 1 inch, and then if you check the brightness, so the brightness distribution changes dramatically. You see, that's why HDR behaves similarly. Okay, dose control precision is achieved using the dwell times with resolution as fine as 0.1 second. Okay, think about that. Okay, the machine can control how long the source stays at each location with extraordinary precision. Okay, longer dwell times means the more dose, shorter dwell times means the smaller amount of dose. Let us discuss applicator here. So the applicators are like a delivery highway, it guides the source to the tumor. Okay, so different anatomical sites requires the different applicator. Okay, depending on the different landscape, you have to adjust the road condition. Okay, similar like that. For example, for gynecological cancer, okay, one of the most famous system is the Fletcher suite applicator. Okay, also known as the Fletcher suite Delclos system. Okay, these are commonly used for cervical cancer treatment involving the uterus or maybe the cervix. So the vaginal cylinder are used especially in post-operative endometrial cancer. Okay, industrial needles are used for the breast, prostate, pelvic, or soft tissue implant. Right. So the rectal applicator may treat rectal lesions, while specialized applicator can even be used in nasopharyngeal region. Okay, so now picture this clinically. Okay, suppose a patient has a cervical cancer. Okay, the tendon goes into the uterus while ring applicators sit adjacent to the cervix. Right, by adjusting the dual position, we can sculpt the radiation dose around the tumor. Okay, while we minimize the dose to the bladder and the rectum. Okay, this is why image guidance is very important in brachytherapy. Okay, so image guidance makes the HDR brachytherapy revolutionary here. Okay, so historically, so the treatment planning relied mainly on the X-rays. Okay, but the modern planning system using the CT, MRI, this is the advanced imaging technique we use now. So why MRI is especially powerful here? Because MRIs visualize the soft tissue beautifully, right? Soft tissue contrast is very good. We can actually see the tumor, bladder, rectum, sigmoid colon, surrounding anatomy much more clearly, right? So the treatment planning system then calculate optimal dual position and the dual times. That's a very important thing here. Think of it like designing the customized lighting system. Okay, in a theater. Okay, a theater where every spotlight intensity and position can be adjusted individually, right? That's how you do here. Let me discuss shielding of the facility design. Very important, right? HDR rooms require significant shielding because the source activity is extremely high. Okay, concrete walls, shielded doors, radiation monitor, warning light, audiovisual systems, all are the essential component here. Okay, so why audiovisual monitor here? Because once treatment starts, nobody remains inside the room. The patient must still be monitored continuously through the cameras and microphones from outside the treatment room. Okay, so the source calibration is very important. So medical physicists always calibrate the source before the treatment. Okay, Before clinical use, the HDR source must be calibrated using the well-type ionization chamber, which is traceable to the standard from organizations such as National Institute of the Standard and Technology. Okay, so the quality assurance in HDR is extremely rigorous. Okay, daily checks, emergency detection tests, timer accuracy, verification sources, position checks, transfer use inspections, right? Independent plant verification, all are mandatory here for the quality assurance process here. Okay, so let me emphasize this strength. So the HDR brachytherapy is one of the powerful tools in radiation oncology, but it is one of the most unforgiving. Why? If mistake appears, if mistakes occur, what happens? So lot of dangerous situation you will face. Therefore, medical physicists play a central role in ensuring the treatment safety and accuracy in HDR brachytherapy. So before I conclude it, so let me ask one final question here. Why has HDR remained so important despite advances in external beam therapy such as IMRT, BMAT, proton therapy, SRS, SBRT? Why? The answer is simple. So the no external beam technology can reproduce the extremely high localized dose achievable by placing the source directly inside the tumor itself. Okay, so HDR therefore combines the physics, it combines engineering, anatomy, radiobiology, imaging, and clinical medicine into one elegant treatment modality. Okay, so in many ways we can say that HDR brachytherapy represents the precision medicine. Okay, before the term precision medicine even become popular. Okay, so so when you think about HDR brachytherapy, do not think only about the radioactive source. Think about it as a careful, choreographed interaction between the physics, biology, technology, safety engineering, clinical expertise, all designed to place radiation exactly where it is needed while protecting the other normal surrounding tissue. Okay, thank you everybody. If you have any questions before I move into the planning examples and the clinical cases, so let's conclude here.